familiarity for like when you
Yeah, I'll probably turn it over. It's like half done. I didn't even attempt the questions.
were they on the
Yeah, which like we just exploded it. I don't know. Yeah, no, that's
oh yeah. I'm just
no, I just want to go home.
yeah.
You can take the test, just try to go as fast as possible. So. That's good.
Yeah.
There we go. Okay. I've just extended the extra homework assignment for a couple, you get a couple more days to complete that, okay? So I think originally it was due tomorrow, but I think it's okay if you submit a week from today, okay? I really want everyone to do this. because I checked the homework grades for this class, and not everyone has 100%, right? I mean, that's clear. So this is the last chance to really get closer to 100% on homework, in the homework grade. So please do it, and let me know if there are any questions, or ask the TAs. They can help. Okay, any questions on that? Anyone who's planning not to do it? I updated the schedule here on Collab. So we are now here, week of Thanksgiving. So as you know, there's no class on Wednesday and Friday. Today, Bassem will take over in 5 minutes and talk about modern MOSFETs. So I'll finish up MOSFET scaling, kind of the problems we saw when we scale down the MOSFET gate length. There were a couple of issues, and he will talk about what has been done and people are doing today in order to make smaller and smaller MOSFETs. Okay, and then after Thanksgiving, we'll do 1 week on the bipolar transistor, and the last day of class is this Monday, so that's 2 weeks from today. And we haven't decided what we do. Maybe Bassem's going to show you a little software tool how you can calculate these things conveniently, band diagrams, current densities, and so forth. And we certainly want to go over the stuff in this class in order to prepare for the take-home final exam. That's going to start on December 4th, after the last day of class, or on the day of the last day of class. And you got 1 week, so submit on or before December 11th. And you can either bring in a paper copy again or submit online. Any questions on the exam? It's going to be very, kind of the format is identical to the midterm. Okay, the questions will be different. But, and it's going to cover the entire semester. Yeah. Yeah. Anyone who's not available during that week? Everyone okay with that? Good. Okay. There's also homework on Collab right now, and I put in the due date is Monday, a week from today. Okay. So, and there will be then one last homework that I'll give on Monday. The due date is then December 4th. Okay. So 2 more homeworks to be submitted on your side. The one that's online right now, and the one that'll cover the bipolar transistor. I'll post it a week from today. Any questions? Anything else? All right. Okay. So what did we do last time? Do you remember? Friday, I showed you these transistor curves. Do you remember what the problem was here with these curves? Hmm? There's no saturation, right? These curves, they don't flatten out. What else? You can't turn them off. They're always on. And what can you say about threshold? Is there significant, well, can you see what threshold is in this plot? No, because it's always giving you a current, right? Actually, it doesn't really matter what you put on the gate. You can go above threshold. It's negative here because we're looking at a PMOS. You get these curves. If you go below or you keep it 0 on the gate, you also get a current, right? You can't turn it off, and that's a serious problem, of course, if you can't turn off your MOSFET. Just think of it as it's often used as a switch also, right? So you want to switch it. So that's a problem, and I mentioned what's called the drain-induced barrier lowering, one effect, and it all comes from the fact, well, that L. Where did we start? I think we stopped here. That L is so short And that's what I used. Okay. Right. It's coming from the fact that this length is becoming, well, it's shorter and shorter. And eventually, something we didn't take into account when we derived the square law, nice formula for the MOSFET, eventually this depletion width from the drain side, keep in mind we have a reverse bias PN junction on the drain side, extends significantly into the channel. Okay, so this part is always depleted no matter what we do with the gate, because this is a reverse bias junction. The P substrate is, or the substrate is only moderately doped. The drain is heavily doped because we want to have, eventually we want to have an ohmic contact to our metal, to the wire. So the depletion width extends mostly into the lower doping, which is the substrate, and here the channel under the gate. Okay, so there's very little depletion width that goes into the N+, because you deplete less in this high doping region. You deplete more on the lower doping side. We already saw that in the one-sided PN junction. Okay, so that has to be taken into account, and it turns out, well, no matter what we do on the gate, this is always, a good portion of the channel is always depleted. Okay, and if you look at the depletion width, you see that, well, if L becomes really short, what used to look like a rectangle for your depletion width under the channel changes its shape, and it looks more like something like this, and it's getting worse as you make things smaller and smaller and L shorter and shorter. Okay, so there's actually some equations in the book, and I'm not going through them. You can actually figure out the change of the threshold voltage coming from this short channel effect, and it's in the book, page 459. There's an equation, so we're interested in by how much does the threshold voltage change as we make things smaller. And what you're gonna find is, if you go through the math, it's basically analyzing that area that I just showed you, okay, and see how that is different from the perfect type of long L, large L rectangle. What you're going to see is that this change in threshold scales with the doping in the substrate, and also with this radius, which is, if you go back to the figure, which is the depth of your drain. Okay, so that length. And then it's also 1 over Ci, 1 over L. So in order to keep that delta threshold small, to make it more look like a perfect long channel MOSFET, well, what do we need to do? Well, you want to make NA small. Well, that's one way. However, at the same time, you want to keep the maximum depletion width under the channel small. So that would actually imply that we make NA large, so we can't really do without, well, putting in more thoughts, can't really do both at the same time. We want to make this depth of the drain side as small as possible to keep R small. That implies using what's called a shallow junction, one that doesn't extend too far in the substrate. And we want to make Ci big. We saw that before. The capacitance of the insulator should be big. That implies that we need to make the oxide thickness very thin, very small, and we've been doing that. Or the other thing, of course, is we could make L big to keep that number small, but that's exactly what we don't want to do because we want to make smaller transistors. Okay, so there are a couple of things, a couple of conflicts. So you can't really achieve everything at the same time, and we'll see what we can do. Bassam will show you in order to fix that. I just want to illustrate what is meant by punch through. The cause for all this mess is that Well, if you have a very short channel, you have the two p-n junctions on the source and the drain side, and there's not even a gate voltage applied here in this picture. The depletion width on the source side is smaller because that's a zero biased junction. This is a reverse bias junction, so we have that massive depletion width extending in the substrate. And you can imagine that either if you crank up the voltage on the drain side and you make L very short, at some point these two depletion widths will overlap, and that's what's called punch through. So what that basically means, I'm not doing anything to the gate, and I'm always depleting the region under the gate, okay? But just having the two p-n junctions, okay? And once this is the case, you will always have an electron flow from source to drain, okay? So there will be electrons, this is slightly forward biased, injected here, and this is a high field region, this is a depleted p-n junction, so electrons will be sucked to the drain. So you will have a nice electron flow that's mostly independent from the gate voltage, and that's clearly not what we really want in a MOSFET. Okay, if you do a detailed analysis, you will find that as you crank up VDS, the resistance here actually in the, well, we can still call it channel, but it's not, it doesn't really matter now, goes down, and the current behaves as the voltage squared, and that's what you see in these messy transistor curves, right? The current is a square of the voltage applied. It's a parabola, right? It goes up here. So that's all beyond punch through, and that's why we see this behavior. Okay, so basically one thing we want to take care of, we want to prevent punch through. We want to make sure that these two depletion widths do not overlap in a short transistor. Okay, and I think that's the last thing, well, almost last thing I have. And so something to keep in mind, starting off with the ideal large transistor, this one here. It is not enough just to scale down the transistor length to make them smaller and smaller, and also to make them faster, because then you run into all these problems we just talked about. So instead, the whole thing has to be scaled down, and that's shown here, where we use now shallow junctions. Okay, that was this one thing. We also need to change the doping in the substrate to prevent that depletion width to extend too far. And we need a thinner oxide to keep the capacitance up. So it's not enough just to scale one dimension, you need to scale the whole thing down. Okay, that's the main message here. And just to sum up, and then Bas takes over, short channel effects, or SCE here. Problem is that the depletion regions at the source and especially at the drain side affect the channel. Okay, we saw that leads to a threshold voltage roll-off, well, which basically says your threshold voltage depends on your transistor length, which is a bad thing. And then there was this drain-induced barrier lowering, where we that's actually kind of showing up as the fact that this roll-off of threshold voltage gets worse at higher VDS voltages. And if you look at the band diagram of a MOSFET, this is a long one with long L. There's no gate voltage here. You see this thing is off, right? You have a barrier here. This is the p-n junction with zero bias. This is the p-n junction in reverse bias. Like you have a nice barrier. In between, there's no channel, there's no inversion yet, so the thing is off. But if you scale L down, you see that the depletion width extends more and more under the channel, so that barrier becomes thinner and thinner, and also lower and lower. And then you can imagine that at some point, carriers can get over this barrier, and once they are here, they see a higher field, and they can make it all the way to the drain side. And that's what happens at punch through. Okay. And of course, you can, if you further crank up the voltage here, this gets even smaller and you get a high current. That's what's this increase in current with VDS. Any questions on that picture? Anything else? Makes sense? Okay, so in order to fix that, and apparently it has been fixed because we have working transistors that are much, much smaller than a micron today. We'll see what has been done. Okay.
To continue off what Andreas was talking about, basically you take the MOSFETs and make them smaller and smaller because you want to fit more and more of them on a chip, right? You want to make as many transistors as you can inside a chip, making them faster, making them smaller. But the more you do that, the more you come into these short channel effects. As he was talking about, we have a lot of problems when you do that. So there are a lot of ways to try to solve them in modern MOSFETs. One idea is they have these halo implants. Basically, you have your drain and your source and your gate, and they basically highly dope right around the drain and the source, basically to control your depletion width. And so by controlling your depletion width, you're basically causing it to not go into the gate length, right? So your gate length is not being affected. So in that sense, you're helping with your channel length not getting to be too small. But when you do that, that comes along with other issues. So when you do that, so if you were to put in that halo implant, then something that can happen is you can get a very high electric field in this region. If you have a very high electric field, if you guys remember, if you have a junction with a very high electric field, you can get breakdown. You can get avalanche effects. So it's basically something that can happen. And so if electrons get enough energy from the electric field in that area, they can actually go really fast and basically avalanche into this oxide. What actually can happen is they can actually get into the oxide and trap into the oxide, damaging the oxide in a sense. So in that sense, the oxide is not as good as it is before. It's not as reliable as it is before. So it kind of actually can cause a lot of issues there. That's called the hot electron effect. So something they do to fix that is they put another doping layer on top of that to make sure that the electric field isn't too high. And so that doesn't happen, to prevent that from happening. But as you can see, that this is just kind of making it more complicated a little bit. Especially in fabrication, you're adding more steps, so it's getting a little more complicated. But, so the idea is you want to make, to get as low of a threshold voltage as possible. Why is that important? It's important because you want as low power consumption as possible in these chips, right? So lower threshold voltage means you need a less amount of voltage to turn the transistor on and get current out of it. So if you make these things smaller, that's better, so you get lower power consumption. So these are the things that you would need to do that. You need shallow junctions, and you need to make sure that you're not getting short channel defects. And so these are some of the ways that you can control that. Right. So usually these things again are done on silicon. So considering that it's on silicon, if you make these things smaller and smaller and smaller, then your electric field is basically your potential over your length, right? So if it's smaller and smaller and smaller, then your electric field goes up. Electric field goes up, that means you're going to hit a certain saturation velocity on your electrons. Your electrons, with a certain electric field, once you get to a certain electric field, they can't go any faster. They've reached a limit. So before, when you looked at these curves, the IV curves for a transistor, they were sort of increasing because of punch through, right? They had a squared relationship. But that actually, in reality, when you make these things actually really, really small, that doesn't happen. It actually kind of saturates, and that's due to the velocity saturation. So you could see over here, on these curves, they kind of actually start to saturate again, which is not necessarily a bad thing, but you are limited by that. And so, something that you need to do at this point, so we said that the main things you want are low threshold velocity, and you want to make these things smaller and smaller so you can put as many transistors in the chip as possible. So another thing that you want to do is to make the capacitance as large as possible and make these things faster and make the threshold voltage lower. So how do you make the capacitance larger? One way of doing that is to make the oxide thickness as thin as possible. So here, usually they used to use silicon dioxide as the oxide layer, but now they've figured out ways to use other materials. And so the capacitance, if you look at capacitance, the relationship between your dielectric constant of the material and the thickness of the material. So if you use silicon dioxide, that dielectric constant is 3.9, but you can use other materials that have much higher dielectric constants, so we'll talk about that too. Another thing, like I said, is to make the oxide layer thinner and thinner and thinner and make the capacitance higher. By doing that, you're actually making the transistor faster. And so this is a year-by-year trend of the capacitance of these transistors. And you can see that they're getting smaller and smaller because they're getting, the capacitance is getting smaller because the transistors are getting smaller, right? And so you want to try to make them as large as you can. Right. So this over here, quantum mechanically, when you're looking at the oxide, if you're looking at just like a metal plate-to-plate capacitor, usually your charges are right on the metals. So like if this is one side of a plate and this is another plate, usually the charges would be just right on the plate. But because this is a semiconductor material, it's actually displaced a little bit because it's kind of like a potential well. Your carriers are actually in the middle of the barrier. They're not right at the edge of the barrier. So that's why there's a little bit of a displacement here. So actually, in reality, your capacitance would be your thickness of your oxide plus that displacement from how far your carrier is from the edge of the oxide. So this is mostly not really to solve the issue of making the oxide thinner, but this is mostly just to make fabrication easier. So one thing they did is instead of using a metal on top of the oxide, they used polysilicon, which is just heavily doped silicon. And basically what this does is, by doing that, that acts kind of like a mask. So you know that that's the gate, and right next to it you have the drain and the source. And the drain and the source you need to dope heavily. And so you need to do something called ion implantation. So basically you're just shooting ions directly at the material, and you want to protect this oxide. So by using this polysilicon material, you can actually just use that as the gate as well as a protection layer or like a mask. And then the reason they use polysilicon is because it has a high melting point. So you can actually, after you do this ion implantation, they usually do something called annealing, which is so you've hit the semiconductor material really hard with a lot of ions. Obviously, it's going to do some damage. So they do something called annealing, which is basically they heat it up really high, and it kind of rearranges the crystal where it got damaged to kind of fix it. And so by annealing, you need to make sure that all your materials can handle really high temperature and that they don't melt. So polysilicon has really high melting point, so it won't melt. And so that's what they did first, and then they actually moved towards using a different metal that actually can handle really high temperatures. So they started using tungsten, and tungsten does the job even better. So anyways, with that said, we're trying to get the oxide layer thinner and thinner and thinner as much as we can, but once you get to, there's a limit for that as well. The physical limitation of that is tunneling. So you guys know tunneling, we talked about before, there's a barrier. In this time, we have oxide as the barrier, and you make this thing thinner and thinner and thinner, your probability of tunneling is higher and higher. So you get more leakage, current leakage. So you don't want current to go through the oxide, obviously, you don't want electrons to pass through. But when this thing becomes thin enough, it's going to happen, you're going to get a lot of leakage. So there's a actually curve here. So Yeah, this is a curve, this is not fully updated, but just to show the trend, more recently you can see the leakage current has really increased with a really steep slope. So the leakage current really is dependent on the tunneling, that's the main source of leakage in chips and CMOS chips. That's extremely important, right? Because if you look at our CPUs and processors, you want to make sure that they're as low power consumption as possible, right? Like your iPhone, if you have your CMOS chips in there and they're just consuming power when they're not supposed to be, your battery life is going to be lower, right? It's going to be basically a lot less efficient than it should be. So you want to try to make these things as low power consumption as possible. You don't want current when there's not supposed to be current. You turn the transistor on, there should be current. You turn it off, there shouldn't be any current. So that's the whole idea. And so there's ways that we have to try to control that. So another thing people do to make the capacitance high is, so we said a thinner oxide, but the other thing that I told you guys about was making the dielectric constant higher and choosing a different dielectric material to do that. You can do that. So they have actually switched from using silicon dioxide to HFO2, which does an even better job of getting the capacitance higher. Another thing they do is they strain the silicon. So by straining silicon, they can make the mobility even faster. So the velocity saturation, we said you're limited by that. If you can make the mobility faster, you can make the electrons go faster. So by straining silicon, you can actually make the mobility faster by doing that. Strained silicon is one option. You can also do germanium, and you can do 3,5 materials like indium phosphide, gallium arsenide. Those are much faster than silicon as well. So you can do that as well, but when you start doing that, then you get a little more expensive. Okay, so this is actually a picture of a transistor. This is not the most modern state-of-the-art MOSFET, but this one kind of uses all what we were talking about. It has a high K dielectric, it has strained silicon, and it has right, and it has the doping where you want it to be the high doping so that you can get prevent short channel effects. So this is just a quick picture that shows all those things being done. Okay, so now I'll try to talk about a little bit more. What are they doing now to try to fix these things? So you guys, I think Andreas talked about Moore's Law, and I'm sure you guys know what Moore's Law is, right? So you want to get as many transistors as possible, but eventually you're going to hit a physical limit. Transistors you're going to get smaller and smaller, and you're going to get physical limitations on top of cost limitations. So they have to, I think at this point they're kind of using, they come up with a lot of cool ideas that they're trying to really force it right now to try to push as much as they can. But soon there's going to be a limit, I think. But some of the things they've been doing now is something called a FinFET. And then there's also a gate all-around. So gate all-around and FinFETs, basically, they use this 3D structure. So they're actually able to build these transistors not just side to side, because the MOSFETs are planar, 2D. So they go from drain to source in this direction. But the FinFET, you're actually doing it in 3D. So you're actually able to get these transistors and you can actually build them on top of each other as well as side to side. So you're actually able to use more real estate on the chip and fit in more transistors that way. Another thing that you're doing is you have a better control of your channel because your gate is surrounding the channel. So you actually have 3 different sides of the channel, and you're actually making the channel length longer than it would typically be in a planar, right? And the longer the channel, the better in a sense, because you're limiting short channel effects. So that's some of the stuff they're doing now. I'm trying to do this really fast.
Take your time.
Yeah, so FinFET is something I think that came out and really started to become used more a few years back. But even the FinFETs now are starting to hit their own limits, and they're trying to figure out what to do next. I think FinFETs are still, so now if you look at your CMOS chips in your computers and your phones, FinFETs are, I think, what are being used mostly in their Intel processors. But looking into the future, right now our current node is 10 nanometer that's being used, and 7 nanometer is kind of what's like right next, coming up soon. Then after that is 5 nanometer node. So the 7 nanometer is kind of like the limit when it comes to quantum mechanics. So when I was telling you guys about tunneling, 7 nanometer is really when you start to hit that limit, and you're starting to get a lot of tunneling due to getting really small. So going 5 nanometer is really a physical challenge, and they're really trying to figure out ways to do that. So they have different ideas of how they can do that. So FinFET and the gate all around FET were some ideas. And so there's a trend here called the Dennard scaling trend, and this is gate length in years, so they're trying to get the gate length as short as possible, like we said. And you can see that we're going even smaller and smaller in the nanometer scale. And after a certain point, we're getting close to I think 5 nanometers, like I said. And you need to have fins to be as narrow as possible. Mobility will help as well if you can make these things faster using higher mobility materials. And different material structure is important. But here's the thing, so considering 3-5 materials are faster than silicon, that's great, but they're more expensive. And also, right now, the CMOS industry is an industry that's been built over decades, right? So all the facilities that Intel has and IBM has, these are things that they've had and developed for several years. People are not gonna restart and try to build all new facilities on new materials. They want to use the existing technology, which is built for silicon. So the idea is they need to try to figure out how to do all this stuff on silicon, because otherwise it would be too costly. And so using 3.5 in some ways can be helpful, but really you need to try to stick in silicon. So there are other, I think, much more future-looking approaches that are very researchy, including what we do a little bit of stuff I think that can help. There's something called silicon photonics, so now you're actually putting photonics on the same chip as the electronics. I think I talked to you guys a little bit about that before. And by doing that, you can actually, so typically you have the transistors are, switching really fast on and off, but there's also the interconnects that are connecting in between everything. So your CPU that are talking to memory, and CPU cores that are talking to each other, as well as transistors that are talking to each other, those interconnects are limiting as well. There's an RC delay associated with the actual wires. And so by replacing those wires with photonics, you can actually make those faster. Other things is quantum computing. Yeah.
How much more efficient are the photonics?
So I think power consumption wise, it saves a lot. It would save a lot. Bandwidth wise, I think it would also save, because you can do something called WDM. So with an electrical wire, you can only transmit one signal on that wire. You can't put several signals. There's going to be interference, electromagnetic interference. With an optical wire, you can put several different signals on the same wire using something called wavelength multiplexing, division multiplexing. So you're getting much more capacity as well as much lower power consumption, because the energy that you're dissipating is being dissipated as light, not as heat, right? So in RC delay, there's RC delay that's associated with electrical wires, but they're also dissipating a lot of heat, right? So these wires, they're getting smaller and smaller, resistance goes up. Resistance goes up, thermal goes up, right? It gets hotter. So you're losing a lot of energy as heat by doing that. So photonics is kind of, I think, the next approach, in my opinion, for CMOS when it comes to interconnects. So that's a field that's being researched, and Andreas is actually doing a lot of work on that. There's also quantum computing, like I said. So that's still, I think, very early in its research stages, but eventually we are going to get to the atom scale, right? We're going to get smaller and smaller. Eventually we're going to hit the actual atomic scale of these crystal structures, right? And at that point, you can't really do this stuff much anymore, because you're within one atom. You can't really split that anymore. So quantum computing, I think, is as small as it gets, as well as it uses, I don't know if you guys have taken modern physics or anything, but like qubits, and you have superposition of states, so you can have an on and off state at the same time. So that actually buys you a lot more capacity in that sense. So those are some of the things that they're going to do in the future, like long term. But things that they're doing now, like I said, the FinFET And then they have, so this is for 22, 14 nanometer nodes, what they've been using. For 10 and 7 nanometer nodes, they're starting to use strained silicon and germanium to make the mobility faster, so that makes it a little faster. Other things that they're doing are these gate all-around transistors, 3-5 FinFETs, and vertical TFETs, or tunneling FETs. So the all-around gate transistors, they're basically little nanowires, and just nanowire is just basically a semiconductor tool that's like within nanoscale, like really, really thin. And they're just surrounded by a gate. So the gate is actually around the whole, I kind of talked about that a little bit before. And then the other things that they can do is 3-5 is much faster than silicon, like I said, so you can actually use 3-5 as the channel. But like I said, that's kind of not so cost efficient. And then the other thing is a tunneling FET. Tunneling FET is a different kind of, is different than the gate all around and the FinFET. So it's kind of, they actually, what they do is they have a, you don't, normally you have a, like a PIP kind of thing going on in your MOSFET. So actually in this case you have a PIN, just kind of like your photodiode and like a PN junction basically. But what happens is you actually have some tunneling going on in between your source and your gate, right in the beginning here. So in the off state, your carriers that are in your valence band are not going to have, or not much of them are going to be able to tunnel through into the gate. But in this case, when you turn it on, you're lowering the barrier, and a lot of these carriers are not actually able to tunnel through this barrier. And so this is actually something that Professor, I don't know if you guys know Professor Ghosh, Avid Ghosh, so he's actually doing a lot of work on this, and he works with Intel, and they're using this stuff now. So it's pretty cool that this is actually stuff that's being used in our chips today. So yeah, those are kind of what's going on now in the modern CMOS technology, and yeah, there's a lot of work to be done. So but then that's about it for me. Any questions? Sorry if that was a lot of information. Cool. Okay.
No questions? Come on, one time. You can ask the question.
Yes.
So, what are some of the huge advances over quantum computing over standardized computing?
I think one of the main things is the whole idea that you can use superposition of states. So one qubit goes a longer way than just a binary.
So it's like 2 to the
Switch
power
is
of
one
n
zero.
more information.
Sorry?
It's like 2 to the power of n more information.
Yeah. So I think that, and also that you're getting much smaller at that point. Because they're
Yeah, I think that's right. You can just code more information into your state if you don't just deal with on and off, right? And so I don't know what exactly is going on. There seems to be one commercial quantum computer that you can buy. It's superconducting, so it operates at 4K temperature. And I heard people saying it's not really a quantum computer, but that's actually something you can buy today. If you Google it, it should show up. And there's some research groups working on these quantum computers now. Still, they're not any better than a regular computer, right? But it's a very different approach. And so this thing, well, and I should know, but I don't. But it is superconducting, so somehow Cooper pairs are involved that form these states. It's not photons. Quantum computing using photons is also one approach, but that's even like early research stage, right? Where you try to entangle photons and then create these very massive kind of quantum states, right? That potentially have well, you can code a lot of information into those. But I guess one problem with these things is very obvious. When you do that, you can't lose any single photon, right? Because you need all the signal you can get, and that basically means no losses at all. And that's difficult to achieve in practice, right? Because if you entangle photons and you're losing a good portion of it, just 10% or so, that thing doesn't want to go. So being able to create single photons in a controlled manner, well, that's kind of possible. To detect them, that's where the photodiode comes into play, is also important, because you want to detect 100%, right? I mean, everything else won't work. And on the way between, well, let's say photon processing, you don't want to lose any photons. And those are the major issues right now to make this happen. People have demonstrated, and there's a physics professor here at UVA, Olivier Pfister, he's working on photon entanglement. So he entangles photons on a daily basis. So if you want to check it out. But he's using huge kind of bench top setups in his lab, right? And you might be able to build a computer in a room like this using photons. But of course you need to integrate that eventually on a single chip, and then things become more difficult. So that's probably, I think as Bassem said, as long as CMOS as long as there's a way to push CMOS further, it'll be done. Even if it costs some money, and it's more complicated, or they need some big investments into the technology, but they will do it because CMOS is so dominating right now, before they switch to some other material platforms or do something completely different. I mean, that'll take a while. And maybe one comment, CMOS scaling or transistor scaling, 20 years ago, people thought they were at the end at Moore's law, right? That there's no way you can make things any smaller. And they said it 20 years ago. They said it probably also 10 years ago. But there was always a way to overcome the problems, right? So this could be just, well, one of those, but we are hitting really kind of the fundamental quantum mechanics. It's not just, we don't have the lithography to make these things so small. It's not kind of a technological issue. It's really a quantum mechanics issue, right? So, but maybe there are other ways. I mean, there's massive research going on into these things because it's so important. So I wouldn't be surprised if it goes on for another 10 years, to be honest. There's a couple of these 3D structures, and what they may do eventually is maybe not switching completely to a different material, but they may gonna use graphene gates or something like that. So put maybe some more material into the CMOS, right? And that's a cost issue and so forth. But basically they can stick to what they have right now. So this could be one way to do it, or maybe also using 2D materials. And, so there are a couple of ways where they can add to the CMOS and push it further, I think.
What are some like commercial uses of quantum computing?
Oh,
Cryptography.
I don't think there's any.
I think cryptography is one big one. Applications, is it?
Yeah, I mean, yeah, just like commercial use. Like, would anyone use it besides like
Commercial.
everyday people use it?
Well, I don't know about commercially, but I know like government would be very interested in for cryptography purposes.
Okay, but that's already available.
And that's
right?
a really
Yeah,
available, right?
yeah.
But
Yeah.
commercially, yeah, that's a good question. I don't know what.
Real
is it
quantum
commercially
computing, well, the hope is it's much more efficient and you can build much better computers, right? So
Yeah.
eventually, well, any application where you need a computer could work.
Yeah.
But right now, just research labs buy these things. And as I said, they're not very powerful right now, but they just use their new approach.
Yeah, you can get more processing power for like if you have a very like processing intensive program on your computer, like MATLAB or something. Quantum computers can help you with that.
Yeah, parallel computing and all these things, yeah, that's the hope. Okay, well, everyone has a good holiday and see you in a week.
I
Yeah, and don't get confused by that, they may just have switched the needles. Okay, so you don't know which one actually hit which side,
Keep
so
counting.
that could be bad. Don't worry about that.
Okay, and also derive the saturation current from the ideal water temperature. So this is the last. Oh, derive the saturation.
That's it.
Oh, I don't have. Well, the saturation current is this, I just multiply by the area.
Yeah, you need to scale it. This is the saturation current density. So you need to-
Also, but it says to compare it to IC, what am I going to compare saturation current?
Should be the same. But I don't call it the same because you're gonna see that the dark current is orders of magnitude larger. They are very different, yeah, and that's correct. So it's just pointing out that the ideal saturation current is super small. You had a quick question or?
Yeah, do you have office hours today? I couldn't find it on the co-op, so I was going to ask. Or like,
I'll be around until the next, well, I'm gonna be around the next hour or so.
oh, okay, 'cause we have class now, but I can just look for the TA office hours. I was just gonna like go through the bonus assignment.
The
Sure.
TAs are the student office and the
Yeah,
CA.
yeah, in there. Okay,
Yeah.
yeah, I'll just go to those.
Yeah, that's fine.
Thank you.
And also when I do the arithmetic factor, can I get rid of the minus one? Yeah, because when I have the plus one here, it looks a little weird.
No, you can ignore that.
Yeah, and so when I do this, for this I, do I do a photocurrent or the dark current?
For the ideality, you wanna use, well, first of all, the problem is, it doesn't make a big difference.
Yeah, they kind of curve the same way.
So it wouldn't make a big difference. It's almost the same.
Good, kind of just want to be precise.
Well, then use the dark,
Okay.
because the ideality factor is defined for a dark situation.
Oh.
If you shine photocurrent, what you see, so the orange one is dark, as you shine light, the whole thing moves down. And if you shine,
Did I?
I'm sorry, move up, I'm sorry. Yeah, it's completely switched, so it actually moves down, but it's on this side it moves down, I'm sorry. So this is dark, this is light, and so in your case it would move up. And if you shine more light, it would move up more. And you would actually also change that part here quite a bit.
Oh.
So your ideality factor would depend on the light you put in, and that's not a very wise definition, so you better take the dark one.
Okay, oh, okay.
Yep.
Thank you very much.
So when we do calculate the ideality factor,
You can ignore the one.
Yeah, sure.
From the top.
5:30?
Yeah, that's fine.
Do you have time for a quick dinner?
You pick a point on the curve, so same here, or maybe you have the same data set.
Something.
Um,
Or you just keep that like
Okay, sure.
Okay, but then it still should be flipped to the other side, but anyway, that's just the polarity.
I'm just gonna.
So you get the ideality factor from this part here, right? When it increases exponentially, and you can neglect this part, this is just a complete, so that doesn't have, there's no information here. But this part, you wanna fit the exponential curve. And so you have voltage and a current for each point.
Thank you.
Yeah?
那一道大题基本没拿分，其他都好。就整个错了很多那道大题，基本没拿分。我没有考虑。对，那门课最近同样用新的课全都是。 这个